considering a matrix Lie group, and here we have a curve in this group which passes through the identity, and now we take the derivative at the identity, and the claim is that these form a Lie algebra, so actually modified with this minus I factor here, which is physics convention. So I call this one here X for the moment. And actually I claimed on the instruction sheet that the Lie bracket for this Lie algebra here is essentially the matrix commutator. So this is a matrix for every t, and these are matrices. So this here is the matrix commutator, and then there's again this minus I factor which comes from here. Okay, so we have to show that this is in the Lie algebra, this object. How do we do this? We start by considering another curve. Let's call it G tilde. So G tilde of t is h times G of t times h inverse. So we take the first curve and conjugate by a fixed group element. Then G tilde at the identity is h times the identity times h inverse, so it's also the identity, which lets us consider the derivative at 0, maybe with a minus I, and the only t dependence is here, so we get the derivative of this at 0, which is just the x. So we get the x conjugated with h, and the x and the h inverse, these are just matrices, so we can define this expression without having to think about that this is in the group and this is in the Lie algebra and so on. For matrices we can define this object here. So we already know that this is in the Lie algebra now. Now let's consider yet another curve. Call it h of t, which also passes through the identity. H of 0 is the identity, and we call the derivative here, we call y. So we say capital Y is minus I h dot at 0. Again, this is a Lie algebra element. And now we define this here. X tilde of t is h of t times x times h of t inverse group element. And now we know already from up here that this object, no matter what h is in the Lie algebra. So here this is now a curve in the Lie algebra. Will be defined here. Takes values in the Lie algebra for every t. Now we take the derivative of this. Where does this live? The Lie algebra is a vector space, so if we take the derivative of a curve in this vector space, we again get something that takes values in the Lie algebra. Since this is a vector space. So we started in the group on a manifold, moved to the Lie algebra, a vector space, and now we stay in this vector space. Okay, what is x tilde dot at 0? Well, product rule, that's h dot at 0 times x times h of 0 inverse plus h of 0 x, and now we have to take the derivative of this at 0, so let's write this out maybe like this. We have h of t inverse d dt at t equals 0. So what is what here? This is I, y. We can see this from here. H dot is I times y. Now this is E, the unit matrix. Here's another E. And what is this? I claim that this is actually minus IY. So y, the light blue thing here, is true, since we can consider h of t inverse times h of t, which is the identity everywhere. So if we take the derivative, sorry, that's not the identity, it's 0, but with the product rule we see that one derivative is minus the other derivative. Okay, but now let's collect everything here. What do we get? We have I, y, x plus, no, sorry, minus I, x, y. So that's minus I times xy minus yx, and that's just minus I, the matrix commutator of x and y. But we know that this thing is in the Lie algebra, and that's actually what we wanted to show here.